All right, so let's run a couple of examples. One that I did in the lecture already, and then another one with more entries, but this one just with Maple. But this, the first one, the first matrix is the one that we did together on paper, so to speak. So the matrix here is 2 by 2. Remember the walking, driving transition matrix. So first of all, let's convince again ourselves that the Markov chain is regular, which means that after you raise the power several times, in this case just only once, all entries will be non-zero. So this is the original transition matrix, and then let's now enter I put some break line here. So let's enter p squared in math mode. So already after second observation, then all entries are non-zero. And so notice what happens if we keep on increasing the power of p. Notice what happens to the entries, how they change, and eventually, if the power of p is big enough, the entries will settle at a fixed value, the so-called fixed probability distribution. So this is p to the power 3. Let's do another one. Let's say p to the power 5. Let's skip 1. Notice they are closer and closer to each other. When I'm saying closer to each other, I mean row by row. So notice the row 1 and row 2 are nearly the same. Because when we reach the fixed matrix, each row will be the same, and each row will represent, like I said in previously, the fixed probability distribution. And so let's say we do 100 observations, so that means p to the power 100. At this point, it should be pretty obvious that the matrix settled at two fixed values, 0.6666 and so on, and 0.33333. So in reality, these are actually 2 over 3, and I don't know, I can't enter, doesn't work here. So 2 over 3 and 1 over 3. I can't seem to move over from one line to another. I just want to show you that if you enter in math mode 2 over 3 in the decimal format, that's the first entry that you see there, and then 1 over 3, which obviously is 0.33333. So that's the fixed distribution, 2 over 3, 1 over 3. Now let's do an example, this time just on Maple. I'm not going to put in the homework 3 by 3 example, but I want to illustrate how this works for any Markov chain with any number of states. So this is a 3 by 3 Markov chain. Notice here again that each row adds up to 1 as it should. And notice that it's not clear if it's a regular or not, because, well, I mean, you'll see pretty soon that it's going to be regular. We have one entry equal to 0, but if we raise m to the power 2, so after one observation only, already all entries are non-zero. So once again, notice the evolution of the entries, compare them row by row, just to see the main idea, right? So if I do m to the power 3, they seem kind of close to each other. Already, if you look at entry 1 and 2 from the first column, it's 0.57, 0.53. And if you get to a very high value, let's say m to 100, then all rows are the same, essentially. So we reach the fixed probability. How do I actually find the fixed probability so that we don't have to raise the power until because it's kind of an intuitive process, and sometimes you will have to raise far too many times, and it's not, of course, by hand. It's complicated to multiply matrices by themselves repeatedly. So the way to find this fixed distribution is again to set up the equation that with a fixed vector, that if you multiply it to the transition matrix, you get the same vector. So this vector that intuitively we produced it here by raising m to several powers, let's pretend we don't know, right, what it is, and let's call that vector or that row matrix ABC. And if that is a fixed probability distribution, then if we multiply the transition matrix, you're going to end up with the same probability distribution. So this is the main property of the fixed probability distribution, and that's where you get the system of equations to find A, B, and C. So once again, assuming A, B, and C will be the final probability distribution, then if you multiply by the transition matrix, that won't change it. That's the meaning of the T times M equals T. So when you do T times N, you get this row matrix, and that'll give you 3 equations, which I put here in the solve command. So the first entry will be equal to A on the right-hand side. There it is. That's the first equation. Second equation will be the second entry equal to B over here. And then finally the last component equal to C from left and right, and that gives you the third equation. 2 of these will be the same. I don't have to worry with Maple to figure out which one is which. That's why you always have to add the condition A plus B plus C equals 1. You always have that extra equation because these probabilities should add up to 1. And then I'll let Maple to solve it for me, and as expected, notice that you get exactly what you see in these rows. So if the question in the problem is to find a fixed probability distribution, this is what you have to do over here in the last part. You don't have to raise the matrix to several powers until it's fixed, because that's obviously not efficient. So I hope that's clear, and that's it for this lecture. I'll see you next time.